afternoon, everyone. My name is Tutugile Kumalo, and I am a part-time administrative assistant at NITheCS. And today I'm standing in for the interim director, Prof. Francesco, to welcome you to our March Mini-school, which will be looking at the parallel computation with GPUs and introduction to programming with CUDA. And we are pleased to have Prof. Martin Bucher and Prof. Japie Greeff. And Prof. Martin Bucher is a NITheCS associate and is a member of the Academy of Science of South Africa, also known as SF, and he has many contributions in the field of theoretical particle physics and cosmology, also observational cosmology. And out of his many accolades, he shared the 2018 Grapper Prize in cosmology as part of the Blank team. And currently he is a director at CNRS in Paris, France, based at the University of Paris. And Prof. Japie Greeff is the deputy director of the School of Computer Science and Information Systems at Northwest, and he holds a PhD in electronic engineering. And his main focus areas are AI, serious game development, creation of technology artifacts which can impact people on a human level, and he's also a NITheCS associate. So I would say we are really grateful to have you give you these lectures, and we hope that our participants will gain a lot of knowledge out of this mini school. And you are not here to listen to me. So over to you, Prof. Martin Bucher, and thank you to the attendees for participating. And don't forget to put your questions in the Q&A page, and we will look at them at the end of the session. Thank you.
Okay, well, thank you for having us, and it's a pleasure to work together with Japie on this course. And we're going to sort of split the lectures and the work, but I'm going to be giving the first lecture. So let me, before going through a lot of slides, just tell you a little about what we will cover and, what we won't be able to cover, since there are only 4 sessions. So CUDA is a programming language that is a lot like C, and relatively easy to program compared to a lot of the first GPU languages, which were people basically used graphics commands, and they were subverted to do useful work. So these devices are easier to program. The course is going to be a bit, well, we wanted to make it hands-on and practical, rather than the sort of theoretical computer science discussion of parallel programming. So we're going to make available accounts for a sort of limited amount of time where, you can work on a GPU, and we'll give you some of the example programs. And I think, the only way to really learn is to, get a chance to play on your own and experiment. So we'll have some theory, but the idea is to get you to try things out. The programming is going to be, rather simple, with examples to illustrate the basic concepts and some of the complexity of parallel programming. So we had some delays. We bought a machine, the GPU card didn't fit, and another solution had to be found. And we should, I hope, next week be able to give you access. The other thing is, at the end of this lecture, I'll give you a link that, well, I guess we can copy it in the chat, where you can get copies of these slides. So the slides are somewhat, keep a record, and some of the text is a bit small, so you might want to go over it. So we'll have more announcements about that next week, and we're sorry we aren't up and running with this practical part right now. Okay, so let's Japie, maybe you could find that link and put it in the chat, because it's quite long, and right now there's just the slides that from today, but we'll put other things there. Okay. So this is a bit putting GPUs in perspective, and so this is sort of a list of the top technology companies, by their market capitalization. So you see Microsoft, Apple, and NVIDIA is number 3. And this is a company that has been growing. So they make these graphics cards, and why are they the number 3 technology company? Well, they or who's paying for the development that allows us to do parallel scientific computing efficiently. So one is gaming and computer graphics. So, and this is how these GPUs, which stands for graphic processing unit, the origin of the name. And then the other thing is artificial intelligence. So the new NVIDIA chips have these tensor processing units, and at low cost you can do AI applications. And that's a little different from what we're going to be talking about, because we're going to be talking here about low-level programming. But this is a company that has grown and grown, and we don't really know where this will go. The CEO, Jensen Huang, said that with AI we're at a tipping point, and there's a lot of hype, and some of it might come true. There might be some disappointment, but this sort of gives you a perspective of GPUs in the economy. Okay, the next slide is has Moore's law, and I just want to sort of explain some general trends. So you would study this in detail in a computer architecture course, but if you look at the orange triangles on top, this is the thousands of transistors, and you can see that there's a log plot, and Gordon Moore predicted that there would be this exponential growth of the number of transistors on a chip, a processor chip. And, that prediction is borne true. And, there are always these discussions. Well, the laws of fundamental physics say that this cannot continue forever. Then there are a number of other things plotted here. The single thread performance. So this is if you just have one CPU, and you sort of see it leveling off. So if you just have a single processor, that they are not getting much better with time. They're leveling off. And then the clock speed is a few gigahertz. So the clocks aren't getting faster. And then in the black, you see the number of cores. So this is sort of multi-core. And I guess the lesson or the conclusion here is that for at least high performance computing, you can't continue to improve single processor performance, where you just have a stream of instructions. So for high performance computing, you have to go to thousands of processors if you want to have several orders of magnitude better. We could talk about the reasons for this, but let's just sort of leave it this is sort of the argument. There is no alternative to parallel computing for the most difficult problems. Another trend, especially in scientific computing, it's quite different what languages people learn. So there's a tremendous emphasis on Python, and which is very easy to program. That's what most people in university or in the sciences they learn as their first language. And then if you talk to people who love Python, they will claim that it's just as fast, and you can use these libraries like NumPy, and there's no reason to use other programming languages that are closer to the machine architecture. And that makes sense if you do stuff like linear algebra, for example. But this is something we were working on that was a tree algorithm. So you have data structures that are not simple arrays, so NumPy won't help you. And we compared Python with, there's nothing unique with this. This is just something I ran, but you can find the, similar examples with all sorts of problems all over the web. So 41 seconds in Python. Then Julia is this new language which compiles code and just-in-time compilation, and it's supposed to be a lot better than Python. And then we tried C and C++, which is a little more messy to program. The .g is the debug option, so the loops don't get unwrapped. It just does what you say. The compiler is not allowed to be clever. And then O3 is sort of maximum compilation, and you see sort of a factor of 50. So there is a reason with certain types of problems to use these languages that are much closer to the machine code, and don't have a lot of fancy intermediate structures. So C and C++ is, you can think of it as an extension of C, is a lot more close to the assembly or main machine code. And, compilers can be very clever and rearrange your code and do all sorts of things. Could execute the instructions in parallel where there aren't any dependency. So if we would go back to that previous transparency, we would find that a lot of this increase in speed is from computer architecture, having a single processor and lots of transistors that do all sorts of fancy rearrangement of the code and that kind of thing. So that's sort of the explanation. So you should just take away, from this previous slide, the orders of magnitude. So parallel computing is not at all new. These are the Craig supercomputers, and they would have vector instructions. So you could do a large number of computations in one instruction and all sorts of tricks. This computer was worth I guess $38 million in sort of approximately today's money, and GPU card costs a few $1,000. So it's something that any research group can afford. So that this is the situation is quite new, that one can do parallel computing with inexpensive commodity hardware. So we're just sort of taking advantage of all the gamers and using their hardware. So this is one of the there was no reason to choose this particular processor, but I just want to give you an idea of the architecture. So this is one of the NVIDIA cards, and it has, I'll explain what a streaming multiprocessor is. I mean, these are processors that give out instructions. So they read the code and go through the instruction counter. And then the, computational units, this is, 4-byte floating point, 4-byte integer, and then, this would be double precision, but you're in the thousands of processors, and now they add the tensor cores. We're not going to talk about tensor cores in this course. So this is sort of a diagram that you have this memory that is shared on the card. But if you can get all of these processors working at the same time, then in theory you could if the speed were the same, you would get, say 3 orders of magnitude. Well, it's not so easy because you need to keep all of these processors quite busy, and you need to know things about the memory. So if you write your GPU program that's correct, technically it'll give you the right answer. It probably won't be that fast. You need to know quite a bit about the hardware. And, if you were writing libraries, you might have some of this invisible, that the properties of the GPU would be probed, and a lot of these decisions would be made without you knowing it. So we'll talk more about this, but this is just to give you an idea of what the difference is. And here I made a list of what are the properties of CPUs and GPUs. So CPUs are really smart. A lot of money goes into a single processor. You might have 8 cores, but you're not going to have 1,000 fancy CPUs on a normal machine. You could at the high performance computing facilities, but that's quite different. So let's see. I have to cover. Yeah. So the CPU analyzes your code. It rearranges instructions. Branches are where the program can go both 2 ways, such as in a for loop. You don't really know what's coming next. So there are fancy ways of predicting which way things are going to go. And then if you sort of have an idea, then you can do some calculations in the way you think it'll go, and then it's wasted. Then pipeline execution of instructions. Instructions are evaluated in parallel. There's microcode where your processor has other instructions that are simpler, and it's more efficient, and memory caches. So you don't really in the usual circumstance, memory access will be quite fast. And GPUs, we have to sort of look that you have thousands of processors, and the price is about the same as a CPU. So they're simple and they're dumb. They don't do all of this clever stuff. So these streaming multiprocessors give out instructions, and generally each core will act on a different set of data, but you save money in transistors in this way. And the pipelining that I described above, a lot of that is absent. There's some other tricks that we'll discuss later. And there isn't this hierarchy of memory. There's some caching. So if you can keep all of these processors busy, and you don't have too much memory traffic, and latency is, waiting for information to arrive, which can take hundreds of cycles, then you can achieve a lot better performance for the same amount of money. So this is sort of this is a summary of, let's see, why isn't it? Oh, okay. Let me hide this. Okay, using GPUs. So this is more for an applications point of view. And I think I need to put this in so that you don't try to program from scratch, problems that you could do much easier with libraries. So using GPUs could be very easy or it could be very hard. So let's take a problem like linear algebra. Well, you can I mean, you have these very simple data structures, and you use libraries, and some of these libraries use GPUs. So you just need the computer with the GPU, and the libraries takes care of everything. So that's not really what we're going to talk about in this course, because there are problems for which these libraries don't exist. And then there are problems where you basically have to write the code yourself and do the parallelization yourself. And, it's quite different from these, Beowulf clusters, for example, where you have lots of CPUs that are, connected, and they each have their local memory. So the cost that those are computers for, data centers or high performance computing centers, and they cost lots of money, and the GPUs don't. So the programming is sort of more limited and a bit harder. Let's see. Okay, let's go a little into the specifics. So graphics cards, started for gaming and the movie industry, and rather than doing it in the CPU, there was special purpose hardware for rendering. So each pixel is sort of a separate calculation, so that that lends itself quite well to what we were describing. And I won't describe this history, but in detail. But in 2007, NVIDIA came up with the CUDA language, and this extends C and C++. So C++ is an extension of C, and there are extra functions and features to allow you to program CPUs without really learning too much. So it's not going to be just as easy because there are lots of synchronization issues. So, a race condition is you have two processors, and suppose the data from one is being used by the other one, and you don't synchronize it, then they race each other, and sometimes one might get there first and another might get there first. So that makes it a lot harder to find errors in the code and you know, getting correct code. Deadlocks is when you know, we put in locks so that different processors aren't trying to write to the same part of memory and creating something that's inconsistent, but you know, one the memory doesn't get unlocked until something else happens, but then the resource is needed by the other processor, so the thing just gets stuck and everyone is waiting on everyone and the program just sort of freezes. Yeah, so we'll talk about tree algorithms. It's you know, something that interests us and how to program it. And there are these atomic operations that atomic means that it's indivisible. It just happens in one swoop. So there are lots of interesting issues, and we'll get to some of them in this course. So let me switch to the more practical, and I'm just going to show you bits of some of our sample programs. So the goal today is basically to get through and show you this hello world where each processor says hello world in parallel, and you can sort of see in terms of real code how this works. So we're going to make full code available to you, and you can go through this yourself, and there are lots of comments, but here I'll just give you some highlights. So this is the let me just yeah, I should have put this slide first. So I want to give you some references, and if you go to the link that Japie showed, you know, you can get these slides in PDF, and you can capture some of these references. So C is a simple programming language. It's a very small language. It was developed in the 70s. It's very it was the Unix operating system was written in C, and low-level programming is still all done in C Linux. And there's this great book, The C Programming Language, which is one of the classics of computer science, and you can get a free copy on the archive. I also included this link from Carnegie Mellon University. So we're going to be using, when you get your accounts, the Unix operating system, so that this, you know, some of you might be more Windows-based, and this is a very short introduction. Then the CUDA programming guide is it's not very well organized, but it has a lot of detail, so that this is a good place to look things up. And I have a number of these NVIDIA references. You don't need to, you know, some of you might know the C programming language very well, and we're not going to use sophisticated features at all. But if you don't understand things, this is where to look it up. There's also C++, but this is the canonical source. You can also sort of Google things, you know, Geeks for Geeks, and these various tutorials are probably better. And then there are the GitHub CUDA samples. So these are a good place to sort of look and study the programs. Unfortunately, they're written a bit for people who are already trained developers. So it's the programs that we will share with you will be simpler than what you find in these CUDA sample programs provided by NVIDIA. But they have some pretty clever things, and you can learn a lot from studying those. Okay, some of this might be review, and this is quite simple. So this is the Hello World program that is in this Kernighan and Ritchie book. And, you know, all the functions are defined in these header files. And C, you need to define everything, declare what the variables are. It's not like Python where you just give values and, you know, everything is completely defined with a type, and that allows for faster execution because there isn't all this checking. So this prints hello world, and I just, for the record, put, you know, how you compile this and run it on the Unix operating system. So what we're going to do on this lecture is we're going to do the same thing. So you have your CPU and the also known as the host, and the GPU known as the device. So this is NVIDIA jargon, and we're going to create 10 so-called threads, and each of them will say hello world. So it's a sort of silly program, but you will see how things are done in parallel in a very concrete way. So you can, I mean, I wrote these slides to have quite a bit of detail, but it's best that you go over it yourself and try to understand it. So I'm just going to here show some highlights. So this is a parallel program, and rather than being a file that is called .c, the CUDA files are .cu, and in a C program, you always start with main. So it's a main program. When you run it, it goes here, and here we print from the CPU, you know, calling kernel function on device. And then this is the function that runs on the GPUs. And there's this new syntax that we're going to have one block of 10 threads. I'll explain what that is. But you have these you know, three less than and greater than signs used as brackets. So this is something that doesn't exist in C. So the CUDA compiler recognizes that this is a GPU function, and that function is defined below, and the underscore global underscore means that the function that you're defining is to be called from your CPU, but it's supposed to run on your GPU. So the same function runs many times, but there's this thread index that is going to be different for each incarnation. So that in one it'll be 0, in another 1, 2, 3, up to 9. So that's how the processes, even though they run the same program, they have their own identity and they do different things. And here what we do is we just, well, if we would just have this printf and this prints out the block ID and the thread ID, hello world from device, block is equal to. So these percent, and that this is a format, this is for a decimal integer. It takes these variables, which are sort of built-in integer variables that from the CUDA system. And if we didn't put this for loop, it's like 10 people talking at the same time. So you're not going to get one message after the other. You might get 10 H's, 10 E's, and then sort of a random arrangement, and you wouldn't get a coherent output. Let's just go back. So how do you run this? Well, you use this, this is the NVIDIA C compiler. So this recognizes all of the extensions, and this is the output file. And then you also have to specify what is the particular device that you're compiling for, because the NVIDIA cards are different and they have different instruction sets. So it can actually create many versions of the code for the GPU card, and as long as you have the right one included, it'll choose the right one at runtime. And here we run this, and it says calling kernel on device, and then it returns, and then with the stream, you get all of these threads in order. So this is the parallel hello world program. So it's kind of a silly program. It doesn't really do very much. There's no data generated, no data transferred back and forth between the CPU and the GPU. But I think the important thing to take away is that you spawn these parallel processes, and then they're distinguished by these variables. So what do we do to keep people from talking at the same time? Well, all of the threads will go through this, and 10 times, because we have 10 threads. And then if the thread index is equal to I, then that's your turn. So it'll write out this hello world to the stream. The output is buffered, so it won't necessarily print out to the CPU right away, but it all gets put in the right order. And we also have to put this sync threads function call. I don't know if it's a function call. The compiler might treat it in a completely different way, but this just looks like C with a few extra features, extra functions that get treated by this NVIDIA compiler in a different way. So the CUDA device synchronize basically waits till all of the streams get sent back to the CPU. And then this code here is just error checking. So if you, the first CUDA programs I wrote, I actually by mistake ran on a computer that didn't have a GPU, and the answers were all wrong, but it didn't crash. It just appeared to have run correctly. And, that's the way a lot of functions from libraries work. They're not going to crash in the middle of the function, and then you need to go to the source code. So this error checking is quite important. And if you want to not write a code that should work, and then you have to figure out why it's producing the weird results. So you want to include all of the error checking. So I think I've let's see. C has a lot of types that are defined in the header files, and CUDA includes the NVIDIA compiler includes header files automatically. So this is actually probably an integer type with an error code, but then there are all these codes defined in the headers. So I will give you a version that you can run yourself and modify if something longer. Let's see. I think, yeah, most of this I explained when we were going through, but I'm going to put extra slides in so that in order to understand what's going on, you don't have to go to references and look things up yourself, because the documentation is very long and not very well organized. So that's why I'm making the slides available. Okay. This is oops, there should be 3 rather than 2. But this is the number of blocks. So you have this hierarchy of blocks and then threads within a block. And we'll talk a little more about this in the future when we do some interesting programs with data. So you set up a grid with threads. So a thread is has its own instructions. It has its own local variables. It also has can have shared variables within the block, and there's a global memory. But we'll get into all of that in some more detail. So these are important variables, the block ID, the thread ID, and here they, take these values. And then each streaming multiprocessor, so that's basically an instruction stream. They do one block at a time, and we can talk a little more about threads and warps and the details of that. Okay, here I explained the synchronization, but I already went through this. So let's see, how much time do we have? About
10 minutes.
10 minutes. So I might not get to the end of this because I would like to take questions, but one thing that we'll find important is, you need to know what your hardware is, how many threads are allowed, how many blocks and all of that, and you need to deal with error handling. So this is important. Let's see. Yeah, this is an example of where we check from these two commands. We get the error code. We look whether if it's not successful, we print an enlightening error message, and you have to decide how much time to put into it, and then kill the program. Let's see. Let me just at the end review a little from C++, because this is where memory management is quite different from Python. So this is that you can find lots of stuff on the web and in tutorials about pointers and addresses. But here we have a floating point number, and we set it equal to 13. So a floating point has, it's a representation of a real number with 4 bytes. And then we define the star means that this is a pointer that points to a float. So this is the memory address of something. And then so an address, if you put a asterisk in front of it, it can also turn it into, the value at that address. But this is just a declaration. Then the ampersand sign gets the address. So here we write the address in memory of this X into Y. Y is called a pointer. And there are two print statements. The value of X is, and this is floating point, the value of the float pointed to by Y is, and then this is the dereferencing operator. So this changes an address into what is the contents. And here we look at the address and print it out. So the %P sign is to print out an address. So on most systems, it would be 64 bits as a hexadecimal number. And then you can see the results, 13, 13, and then 0x is the preface if it tells you that what follows is hexadecimal, and this is the memory location. So this would be good. I mean, some of you know this, but if you don't know this, you should look through this example and make sure that you understand it. And here we define an array and we do some pointer arithmetic. And so you can add a number to a pointer and it'll just shift the address. It knows that it's a pointer to a floating point number, and you get the same result. So you should understand this. And here we allocate arrays. So we malloc, which is in the standard library, will return a pointer to space for then here are 100 floats, and here's the output. So this would be good to go through. And here I'll just close with a sort of semi-humorous comment that people in Java and Python, pointers cause a lot of confusion and can cause a lot of problems and weird behavior. So there used to be a lot of arguments that pointers are the root of all evil, or programs using up all of the memory, and they're not allowed in certain languages. So we will use a lot of this to transfer data from the CPU to the GPU. So you should master this for C, and then we can look at that. So I'll stop here and take some questions.
I've been answering questions in the Q&A. So I think there's one that would be useful if you just go to the slide with your code.
Which one?
So the one that's in the Q&A at the moment by Analapa Roy. So the first program that you showed, the Hello World one, this one.
This one?
Just forward.
Or the parallel
Yeah.
Hello World?
Okay, so the question is, in this Hello World program, what if we ran the for loop in the main and passed the count I as an argument to the kernel? Then the control instructions are the CPU, not the GPU. Would that be faster or slower?
Well, I think it would be slower. So the communication between the CPU and the GPU is not very fast. Whereas here it's the synchronization is on a chip, but I think that suggestion, you would be launching a kernel which would have 10 threads, but only one thread would do something at a time. So it would create correct code, but it wouldn't really be parallel. It wouldn't. Yeah. So you could do that, definitely. I agree. Kernel launches are also expensive.
And then the other 8 questions I've already answered. So I think we made it just in time for 3 o'clock.
Any
Any
additional questions? Or comments, things that you're interested and want to know?
Oh, there was one question that perhaps you would answer that I couldn't. There was, let me just get the person's name. Japie says he has a Fortran 77 code that is running pretty slow on big problems. Is it possible to make it parallel and make use of GPUs? And if so, where should he start searching? Do you know of a Fortran 77 to C converter, or how to link C libraries that you can do in CUDA with Fortran?
I'm not sure. I don't believe that there's a Fortran version of the code, but what you could think about doing is, and I mean, most code, there are just a few critical sections that are, take a lot of time, and most of the bulk of the code doesn't really take that long. So you can do mixed language programming, and then write the part that uses the GPU in C. It would be a bit complicated. I mean, you might just consider rewriting the whole code in C and C++. And I guess you would have to look at the NVIDIA C compiler and see how you can, combine things, but you might be able to do that. I believe the new Fortran compiler converts the code to C. And then I guess the other piece of advice is to just Google your question, and there's probably something on Stack Exchange or the NVIDIA developer forum where somebody has tried to do what you're trying to do. I mean, I doubt you're the first person who asked this question, and nowadays with most computer problems, if it's a bit non-trivial, the first place you go is on the web and try to find somebody who has done similar things or ask the same question, and that's a good way to get the answer. So that's a long way of saying I don't know.
Okay. And then we have a lot of people thanking you for the talk. And Tutukile, I think over to you.
Yes, thank you so much, Prof. Martin, and thank you, Prof. Japie, for answering the questions. I think you missed one that was in the chat.
Which one?
It says, so far I see the discussion is C-based codes. Do you have plans discussing CUDA examples with Python codes in future sessions?
Yeah, so Mahbub did ask that question in the Q&A as well. So
okay.
We bring Python CUDA programming in this course, but I did add a link there to a tutorial on using Number, which is how you would use CUDA inside of Python.
Okay, I guess that's everything. Thank you again for taking time out of your busy schedules to give this interesting and very insightful mini school. So thank you again. Have a lovely afternoon. We will meet again next week, same time.
Great. Thank you very much. Thank you,
Thank
everyone.
you.
Thank you.